In this session, I will show you how to perform a basic DTA simulation using DynuStudio. Before I actually run DynuStudio, let's review some basic setup for the modeling. The first one we want to review is the user class definition. In this dialog box, it shows for the three basic mode, SOV, truck, and HOV. So we need to specify whether for each mode we have using the separate demand table or we're using the combined demand table. In this case, since we have a separate OD table for each mode, so we are selecting the separate demand. So we check the truck, HOV, the selection button here, and we also, and then the total combined of three tables should contribute to the 100% of the demand. Then for each demand, we will need to specify the distribution of the traveler class. In DynuStudio, we have 5 built-in classes. So the first one is a historical user class. Basically, this is the behavior definition. So it means for the historic class, that means those are the people that always follow the usual travel path, and without is insensitive to the for example the VMS, the variable message size. The second class, user class, is the assistant optimal. In this case, DynuStudio currently disabled this class. So this class is this option is grayed out. The third class is the user equilibrium. So those are the users always search for the best path for traveling, and also assuming they have the full information to make decisions. So in this case, we are assigning 100% of the demand to this class. So this is a user equilibrium class. Another one is the en route information. So those are the people that they can change their path along the way when they see if there's a congestion ahead, so they can divert using the detour routes. The last user class is the pre-trip information. So those are the people they are sensitive to the variable sign. So when they travel, they're assuming, if they see the sign down the road, they will make a decision accordingly. So then we need to, since we are assigning 100%, assuming the 100% of the class is user equivalent, so we enter 100% here for SOV, and we'll also assume for truck and the HOV modes, they're also using the same percentage. So that means we are assuming 100% for all the three modes. So once we are fine with this setup, then we can close this dialog box. The next information we need to review is the variable time. So the variable time will determine how each vehicle, how each user will respond to the tolls if the tolls are used in the network simulation. So they also we can attach each value of time to each different mode. So for example, in this case, LOV or SOV is $10 per hour. Then HOV is $15 per hour, and the truck is $30 per hour. Usually, HOV truck have higher value of time than the SOV, and the truck is usually has the highest value of time. Then another factor we need to specify is the freeway bias factor. In this case, we are entering 10%, so which means the perceived time for using freeways is 10% lower than using the arterials. So those are the factors need to be calibrated during the model calibration process, and also can be collected from travel surveys. Another important information for DTM modeling is the speed flow curve or the traffic flow models. This is similar to what we used in using the BPR function in the static assignments. In static assignment, we are typically using VC-based curves or the BPR curves, but here we are using the speed density curves. That is the fundamental curve defined in traffic flow theory. The curve can be divided into two major categories: the two region and the one region. The two region representing the freeway systems, and the one region representing the arterial systems. So in two region curve, we have a flat section between the zero density to a certain density. For example, in this case, it will be 25. The 25 vehicles, density is 20. So when the density below 20, then all the vehicle can travel at a free flow speed. Then after the break point, then the speed will starting to drop as density increase. The vertical axis representing the maximum flow rate or the capacity then can be reached for a link. And there are two parameters are used to determine for the curve to define the curve, the alpha and the beta. If you decrease the alpha value in this case, then you will see the curve will become flatter, so indicating the maximum capacity is starting to increase. When you increase the alpha value, then the capacity or the maximum flow rate will respond to the different direction, so we're starting to decrease. So, and we also have another term is the beta term. So the beta term will determine how fast the curve will, how fast the capacity will drop or increase. So the value for the value for beta is between 0 and 1. So both alpha and the beta value can be calibrated using the observed traffic count data, specifically the freeway loop count data. And this is one of the major calibration work during the DTM model development. The speed density curve can be also viewed in another angles using the speed flow curve representation. So here you can see the vertical representing the speed, and the horizontal axis representing the maximum flow rate. And also we have another side of the vertical axis representing the density. So you can see as your density increase, your flow rate was starting to decrease, and then there will be a curve around to the maximum point. After the maximum point, so usually when speed reached at 45, it has the maximum flow rate. Then after that, then you will be your flow rate will decrease. You can see when your speed drop down to 45, then it has the maximum flow rate. And after that, your flow rate was starting to decrease. So this is basically another way to see the capacity relationship, speed and the capacity relationship. So this is another angle for another view using the speed density curve representation. So the dashed line actually representing the speed flow curve. And you can see the curve, speed flow curve there is the maximum point there. So that usually correspond to the 45. Usually is between 40 or 45 density points. That's the maximum flow rate, or that will be the critical density. In this case, you can see the critical density is 44. You can have as many traffic flow model defined for a network. So it's basically give you more variations to represent different link types. For example, you can have a traffic flow model differ for collector arterials, major arterials, and also the freeways. The major freeways and also the freeway ramps, on ramp, off ramp, they all can have a different traffic flow models. Okay, let's close this dialog box.